Hello, I am Dr. Budhaditya Hazra, an associate professor in the Department of Civil Engineering, IIT Guwahati. I happen to be one of the organizers of this beautiful conference, Adrita Adrabhumi, celebrated on WWD, that is World Wetland Day. Now, this talk is specially dedicated to my students, on whose request I have agreed to present some of my thoughts on probabilistic modeling of wetlands. I am not an environmental engineer or an environmental scientist per se. I am a structural engineer by profession. But over the years, my interests in applied mathematics have allowed me to connect various aspects of modeling across different multidisciplinary domains, including environmental engineering, which brings me to this talk. I welcome all the delegates and the participants to this beautiful conference, and the subtle message that I would like to convey through this talk is that my dear students do understand that modeling the wetlands is one of the most intricate subjects that you can ever face, because it involves so many different types of interactions: physical, chemical, biochemical and physico-chemical interactions. And in order to do justice to the modeling, mathematics should not be spared, and it is the only tool that allows you to reach and cut across all the domains. I'm giving this talk as because I've promised to my students that I will present a talk, for this conference, which celebrates the World Wetland Day. The title of the talk is Probabilistic Modeling Aspects in Environmental and Water Resources Engineering. Well, my area of interest actually it arises from the mathematical underpinnings of civil and environmental engineering in general and structural engineering in particular. I am a practicing structural engineer, but of late, all the allied problems in the applied mathematics and mechanics domain, cutting across the various disciplines of civil, mechanical, environmental sciences and electrical engineering interests me a lot. So taking a cue from that, or basically with that connection, I am able to present this talk. So the whole idea is to tell my students that in this modern day, where the demands of technology are steeply increasing day by day, that is demand of innovative technologies, and at the same time conservation of natural resources is a huge problem, a burning problem. It is very important that they are aware of the mathematical demands or the mathematical skills that are needed to solve most complex problems. Typically, I'm going to talk about three problem statements, which I have been involved partially, if not completely. The first one being the probabilistic modeling of seepage flow, not in a particular order, I would say. Then stochastic dynamics of BOD and self-purification, and stochastic modeling of wetlands, which is the theme of this beautiful conference, Adrita Adrabhumi. So without any ado, I would like to jump straight to my talk. Basically, I would like to motivate that in the modern era, where the modeling problems in civil engineering, why civil engineering across all the branches of engineering are becoming so complex day by day, that it is not possible to deterministically model all the cause and effects, inputs and outputs, and all the interrelationships between the various parameters and variables in a mathematical framework. So uncertainty, starting from quantum mechanics, for example, that is theoretical physics, to all the way down to machine learning, the applications in stock markets, is one of the most inherent feature. That is uncertainty, or I would say probabilistic modeling is one of the most sought after tools to address a wide range of these problems. So I would start with
A very simple example of a stochastic modeling of wetland, which was presented by Bertesolo et al. In 2018. Okay, it's a very nice paper and it kind of motivated uh, the food for thought for my talk. Is if we try to model a geographically isolated wetland, right? Using the inflow outflow, that is the inflow happening through rainfall and groundwater recharge, and of course outflow losses that can happen through you know evapotranspiration, and of course there are other ways, many other ways by which we lose water these days. So if we try to see this problem and we try to address the mass balance, that is the inflow and outflow quantity of water balance, then the first order differential equations can be easily arrived at, and it's a very standard textbook telltale problem which can be solved without any fuss. But what gets really fussy is the fact that rainfall is a highly uncertain phenomena, and with this climate change looming large upon us, it has become ever so difficult to model it deterministically. So these rainfall influxes, these are essentially stochastic processes. And thus, this differential equation is no longer a deterministic differential equation, but a stochastic differential equation, right? So the first input term on the right hand side represents stochastic water inputs due to a sequence of rainfall events, right? So with this motivation, which is already provided by Berticello at 2018, let us see how we can address this problem using the basic techniques of differential equations and extrapolation to stochastic differential equations. So the first step is modeling the dynamics with stochastic differential equations. Now, in order to do so, first let us consider an ordinary differential equation, which most of the engineering students know very well and understand very well. We engineers understand differential equations so easily. But then let us add an uncertain term or a white noise term on the right hand side, so that this ordinary differential equation becomes a stochastic differential equation. So now if we generalize this a little bit by adding a multiplier matrix, what we have is a proper diffusion equation. And the techniques that are required to solve involves what we call as Ito or Ito calculus. Ordinary differential and integral calculus is not good enough to solve stochastic differential equations. So we therefore need a new branch or a new way of looking at calculus, which is called as the Ito calculus. So the starting point of Ito calculus is the Wiener process. I mean, we have forgotten. I mean, people talk about Einstein, Albert Einstein, for different reasons, but his PhD thesis, if we remember, was on this topic, which is called the Brownian motion. Right. So the starting point of Ito calculus is something called a Wiener process, which can be defined as a stochastic process whose generalized derivative is white noise. That's the most simplest definition I can think of. But of course, there are some mathematical complexities and it cannot be simplified at this point in time. And it requires a little bit of more background. So what happens, the differential equation, then it translates to what we call as a diffusion equation or a Langevin equation, where the first term is a drift term or a deterministic component and the second term is a stochastic component. So differential equations, as we know, in order to solve them, we need integration techniques. That is an ODE. If it is an ODE initial value problem, that is where the boundary conditions are provided in terms of time or initial conditions. So initial value problems can be easily solved, or a combination of initial and boundary value problems, mixed type of boundary value problems, can be easily solved using ordinary integration techniques like for example shooting method or Runge-Kutta fourth order method or Taylor series based methods. Now this same idea, it can be extrapolated to uh, stochastic differential equations, and the scheme that we end up using is called a Euler-Maruyama scheme. So the Euler-Maruyama is the simplest stochastic integration scheme that is used to solve these stochastic differential equations. Now, coming back to that, GID, geographically isolated GIW problem, modeling problem, that is geographically isolated wetland problem, the stochastic problem. So what we have is indeed a stochastic differential equation. So in order to simplify that understanding a little bit for the environmental engineers, if we consider the stochastic BOD problem, biochemical oxygen demand problem, which is well studied problem, or which relates to what we call as self-purification in streams or rivers. So here in the first order differential equation, we can easily add an uncertainty term that arises due to white noise or Wiener process, or the derivative of Wiener process, which can then be written in the form of a differential equation, and one stochastic differential equation in the form of dBT is equal to some constant into dt plus some other constant into dWt, which is the general format of stochastic differential equation or the diffusion equation, which can be solved using the standard Euler-Maruyama technique. So here, for a particular case of that stochastic BOD problem, if we account for the uncertainties, this is a MATLAB program which I ran for the previous, the problem given in the previous slide. And when I solved it using stochastic parameters, that is the stochasticity of the input or stochastic input term, what we see is the trajectories, they have an associated or an inherent randomness about them. That is the BOD curve, instead of following an exponential decay, it well, on an average, it still follows an exponential decay, but there are random fluctuations around it. So the mean of it, as you can see, this mean of it is shown by that red line, and it can be, simplistically stated that if we solve the deterministic problem, we would actually end up getting a trajectory that is close to the mean. So this is the power of stochastic differential equation. This allows you to study the uncertainties or the fluctuations around the mean in the most general framework. Now, a more overarching and slightly complicated problem, and I'm not going to take a lot of time to talk about it, is the stochastic CBOD problem, that is carbonaceous biochemical oxygen demand problem. Now, it's a slightly complicated problem because which is widely used in water quality modeling of rivers and estuarine systems, and perhaps our great Brahmaputra that we have here. It can be solved by using an extension of Streeter-Phelps model. In this model, CBOD, dissolved oxygen, and nitrogenous biochemical oxygen demand are related to each other by using, again, a first order differential equation. Sometimes we call this as a state space or a state equation. Now, the main problem of this is that, or the major problem is that the parameters are very hard to determine in practice. As you can see, there are many parameters, right? All the reaction rate coefficients, then photosynthesis of oxygen, respiration, then independent sources. So all of these parameters are very hard to estimate in an experimental framework. So what is the result? What is the way out? Is it might be more realistic to incorporate some level of uncertainty in the model, which can be done by modeling uncertain parameters as stochastic processes. So the most convenient way is to add a white noise to the constant part of each equation, and that effectively turns the deterministic equation into a stochastic one. So what we do is, we have seen the deterministic equation, which is basically the drift part of the diffusion equation in the previous slide while talking about the CBOD problem. Now, what we have to do is just add this little boy in the the red box. I would jokingly say the little boy in the red box is basically the devil here sitting here, which is the the differential of Wiener process, or the white noise term. So now I would shift the focus to another problem which is widely addressed in environmental and water resources engineering, is the seepage modeling. Now, this is one of the problems that I am directly involved in solving, because very recently one of my students, Dr. Atma Prakash, he actually addressed this problem in great deal of depth. So I will pick up one small nuance of it. So the seepage modeling, the seepage problem, as we know, is basically an unsaturated flow problem. That is, the seepage flow typically happens in an unsaturated medium, which is the most practical medium of soil, or soil and plants, or soil plants and bacteria, or soil plants, bacteria and geomaterial, all put together. Right. The simplest modeling equation is Darcy's equation. Now, one of the closed form solutions for steady seepage is provided by Gardiner, which is in the form of this expression. To cut the long story short, this kxt is a term which we call as the permeability, right? It's the unsaturated permeability, which can be expressed in terms of ksat into e to the power alpha x into the head. hxt is the hydraulic head. Now, after solving for hxt from the above solution, one can find out the kxt, and these are the different parameters. K is the hydraulic, small k is the hydraulic conductivity, and several other parameters which you can read up, right? So here, this shows the simulated random fields of kxt, that is the permeability and the hydraulic head, as a function of depth. Now, these simulated values are actually emulated from real data which was obtained from Borden aquifer in Canada. So here what we have done is we have modeled permeability, unsat permeability, in terms of depth. That is, it is expressed as a random variable in space rather than random variable in time. So random variable in time that evolves in time is called random process. A random variable that has got special connection or special relationship, or that evolves in space, is called a random field. So typically, Frank, Clayton, Gaussian, and Gumbel, these are different popular random variables that express different types of association. By association, I mean nonlinear correlation. So based on the data from Borden aquifer, once log k is modeled using the random field, it is simulated using different copulas, and on the right hand side, the nature of hydraulic head as a function of depth is shown for 1,000 realizations. So now this can be applied to solve the problem of unsaturated slopes, stability of unsaturated slopes. Now, this wetland, our Adrita Ardhrabhumi, which is the great wetland in the basin of Brahmaputra, it is endowed or gifted with many slopes, infinite or finite slopes, and slope stability is of grave concern, typically during the rainfall or the rainy seasons. So one of the more practical problems to solve is the unsaturated slope stability. Saturated slope stability is a slightly simpler problem to solve, which is why this problem interests us a little more. The factor of safety, it can be expressed in terms of this function, where we can see there is a function called C psi and gamma s. The psi is called the suction, and C psi is called the apparent cohesion. Now these parameters are described in this table, as you can see. And for estimation of apparent cohesion and not the actual cohesion, there was a model proposed by Liu and Griffiths, which is used here. The failure probability can be calculated using the standard indicator function approach as the relative frequency of the slope failure. That is, when factor of safety is less than equal to 1, it means the slope has failed. And in a Monte Carlo setting, what we have to do is use a counter or a count the number of times factor of safety is less than 1, sum it up and divide it by the number of instances. Simple relative frequency approach. So this shows the plot of factor of safety versus depth for different types of copulas or different types of nonlinear associations. As we can see that nonlinear associations are very important because, for example, if it is a Gaussian copula, then the factor of safety goes below 1 for Gaussian and Clayton, whereas for the other copulas, Frank and Gumbel, the factor of safety stays above 1. That is, in other words, the slope is stable. So if we choose a different type of association for all the other parameters remaining same, a different type of nonlinear association, it presents us a stable slope, whereas another choice, or a rather unfortunate choice, which is the Gaussian, for example, it tells us that there is a slope failure because it is going on the other side of 1, the left side of 1. So with this, I would like to end my talk with a vote of thanks to all the participants, the organizers, all my fellow colleagues from Cotton College, and all the students who are presenting their papers, all the organizing committee, everyone, uh, mm, for patiently hearing this talk and making this conference a great success. And with this, I would like to end the talk.